today I have a lot of material. I think we are not going to be able to go in detail in all of it, but hopefully we will have enough time so that you get the equation. So yesterday we saw some examples of things that went not that well in some real applications, and then we translated some social and legal definitions of fairness that already exist into some sort of quantifiable measures that almost by the end of the talk we managed to translate in some statistical conditional independence. So basically, why I decided to represent all these definitions like disparate impact, disparate mistreatment, or even calibration per group as conditional independence was because it's going to help us to formalize trade-offs and impossibility results. So just as a summary, remember that at the end of the day, all the definitions that we saw can be written as some statistical independence between these three variables that we have here. Just as a reminder, we have the sensitive attributes, we have the target that we are trying to predict. So far, we have called it label, and the prediction. And basically, one definition or another is assuming that the sensitive attribute is independent of one of these other two variables, potentially conditioned on the other one. So, coming back to today's talk, in principle, from a social point of view, what we would like to do is to have a system that is fair in any sense, right? So if you would talk to a policymaker and you say, which definition of fairness you want to apply, they would tell you everything. We make sure that the system is fair in any regard. And this is exactly where the next results are going to come in, which actually show that achieving several notions of fairness or fulfilling them at the same time is actually not possible at all. So basically, if we think of independence and sufficiency, which also can be seen as achieving demographic parity and statistical parity in the predictive rate, is not possible. So we remember that we have three definitions, so one pair is already broken. The second one is that if we try to ensure independence and separation at the same time, that is again demographic parity, but in this case equalized odds. That's again not possible. So we cannot achieve the two of them at the same time. So we have now two pairs in the triangle. And the last one, unfortunately, is also not achievable. So we cannot achieve separation and sufficiency at the same time. That means we cannot achieve, for example, equalized odds and at the same time has parity in predictive rates. So I'm not going to really enter in the proofs, but you can see them here because it's simply a bit of playing with random variables and statistical independence, and it's very easy to prove that actually you cannot achieve any of these pairs of fairness at the same time. That means that if I cannot fulfill two at the same time, it's not possible to achieve the three at the same time. That's going to mean that you are going to either need to pick one definition of fairness that you want to fulfill, or there is always going to be a trade-off. Maybe I want to achieve this level of statistical parity, not really parity, but remove it to some extent disparate impact, and at the same time have the errors rates per group under control, right? But there is always going to be a trade-off because achieving the three of them or two of them perfectly is always impossible. So simply as an example, I basically placed an example between equalized odds and predictive rates. I'm not going to enter into that because it's a bit time-consuming for the information that it counts, but it's in the slides that you all have in the GitHub. But something that is also important is that it is not that there is always going to be a trade-off or some impossibility result between fairness notions, but also every time we want to achieve one fairness notion, we are usually going to have also a trade-off with accuracy, which is usually the main objective that all of our methods tend to be trained for, right? So we usually do empirical risk minimization or minimum expected loss, which also translates into maximizing accuracy. How much we are gonna need to sacrifice in terms of accuracy or any other measure of performance on our system when we wanna achieve some level of fairness is gonna depend on many factors. So it's gonna depend on the data. That means how we were saying that all these definitions of fairness is at the end of the day conditional, statistical conditional independence, right? So the more dependencies there are in our data, the more likely we are to lose things in order to make them independent. So in general, what we can do is to think of this trade-off of fairness and accuracy as a constraint classifier. So usually what we do when we do learning on a supervised setting, in many cases, not always, is to maximize performance, to minimize loss, for example, or maximize the minus loss. And now, instead of finding the best solution among all the potential solutions, which is no more than parameters, right? Okay, so now we are going to need to restrict our space of solutions. That means, for example, the parameters of the classifier, the parameters of the logistic regression, to only those that fulfill our fairness constraints. So here, we are going to have some fairness constraints which need to be below, or unfairness constraints that need to be below some alpha. This alpha parameter is going to allow us to have a control between this trade-off between performance and fairness. And in general, this is something that, as a developer, I don't have control on, but this is something that might be imposed by law. So there might be some laws that say your level of unfairness in some of these definitions shouldn't go below or beyond this value, or by the system administrator. So maybe the system administrator, the bank, wants to achieve unfairness, some level of fairness, but maybe not at any cost. Maybe they want to keep the investors still happy, right? So this is always going to be a bit of a problem. Keep in mind that we are going to all have very different trade-offs between fairness definitions and accuracy, which are going to make everything a way more complicated than the standard machine learning framework. So the question is, okay, now I have data. Yeah. Yeah, so that's true. That depends on what is your measure of performance, right? And this is, I'm not entering very much into that from the point of view of fairness, more from interpretability, but there is something called stakeholders, right? Which is basically you have the system administrator, you have the law, the justice system, and then you have the individual users, right? Their level, their measure of performance in general is going to be different. The bank might want to be rich. The court wants the system to be socially fair, right? And the individual wants the best benefit for them, right? So if you think about it, while in machine learning we tend to have only objective function, which usually we measure as accuracy, when you extrapolate that into society and you try to develop the system, you have different objectives that you would like to achieve at the same time, right? So this moves a bit away from the standard classification setting that we have. Yeah, you have a very good point. So, but for now, let's assume that we still want to, that we are, we are part of the system. I'm the developer of the system administrator, so I would like to be fulfilling the law, right? And be fair towards people, but I still want my profit, right? So this is where this kind of formulation makes more sense, because I would like to still be under the low constraints, but still maximize my profit. So how do I do that? We talked the other day that there were basically, depending on the definition, there are three main ways of achieving fairness in a classification task. The first one is to pre-process the data. Then we have post-processing the results of this classifier, or we can change the training of the classifier, as I was showing in the previous slide, where we were training directly with some constraints. So in terms of pre-processing, what people have been mostly doing is that given your data, with your features, your sensitive and non-sensitive features, what you would do is to map this data into a new representation that fulfills some fairness, that remove some of these statistical dependencies between the variables. And then they would use this representation in order to train the classifier. That means, for example, for the people familiar with representation learning, would be mapping your data into a representation that basically contains as much information as possible about X, but as minimum information about Z, and then use this new representation of the data in order to train the classifier. There has been several approaches for doing that. The first one that was proposed was by Zemel et al., and basically they translate that problem into an optimization problem, which is quietly related to a clustering problem, in which basically what they did was to find some prototype vectors, they call them, that actually represent the data and assume that somehow the distribution of which data were represented by each prototype were independent on the sensitive feature. Here you have the general formulation. It's not particularly important beyond the fact that whenever you do that, you always need to account for the different objectives. So the first one, we have here different losses. This first loss, which is at the Z level, is somehow the one that is going to control for the fairness definition. So in general, it's going to be for this parity impact, for the statistical demographic parity. The second one, I'm sorry that it should be X. No, it's X. Sorry, I don't see it from here. It's basically an error that is going to account for how much information the new representation of my data has about the former X, the former features. You want to keep as maximum information as possible. And the last one, loss, is about how good I'm going to do in my prediction task using the new representation of the data. Of course, you can solve that problem in many different ways. This is a very naive way, the first one that was introduced, but there has been some other approaches based on, for example, variational autoencoders or adversarial training that basically try to balance the trade-off between all these losses and find representations that jointly fulfill these three main properties, which is let's have as much information as X, the non-sensitive features, as possible, the least information of Z as possible, and at the same time be discriminative with respect to Y. Good. The problem, I mean, there are pros and cons of this method. The good thing is that once you have pre-processed the data, in general, it doesn't need to matter for which task or which classifier you are going to use, at least not which classifier, so you can pre-process the data and try different classifiers. Other good property is that once you have transformed the data, you are not going to need access to the sensitive attribute at test time. That's going to imply that you are not going to suffer from disparate treatment. Remember that disparate treatment was related to direct discrimination, and it was the fact that you were using the sensitive attribute in order to make the decision. On the contrary side, on the bad side, is that this kind of pre-processing step is only useful for some definitions of fairness, in particular for demographic parity or independence, we call it before. And also, I think it's quite obvious that we have a complete lack of control between the representation in general, the representation that we are going to have, and the trade-off between fairness and accuracy, because if I use this representation for any classifier, maybe I have an account for which classifier I'm going to use during learning this representation. Otherwise, it's not model agnostic. As a second solution, which was mostly proposed for equalized odds or equal opportunity, what you can do is that I don't touch the data. My data are the only ground truth that I have. I instead train a model and I correct for the predictions of this model so that I balance whatever quantity I have to balance. For example, the error rates. So, in order to do that, if you want to... Okay. In order to do that, if you want to achieve equalized odds or equal opportunity, so everything that you need to do in the case of equal opportunity is that basically you plot your ROC curve, which basically has the true positive rate in front of the false positive rate. You have the ROC curve here, right? And what we know in general as a result in machine learning is that the tangent, the point in which you can make a tangent pointing out towards the opposite direction, like exactly this perpendicular point, this point is actually the optimal point for the decision threshold. That is going to give you the best trade-off between true positive rate and false positive rate. If now you apply that and you separate the ROC curve for both the females and the males, what you can find is that the intersection between these two ROC curves is going to give you the best solution in terms of accuracy that fulfills equalized odds at the same time. It may still happen that these two curves don't actually cross to each other, and then you need to find the point in which they are the closest as possible, and then in order to achieve completely equalized odds, you are going to need to include some randomization to correct for this mismatch. So, yeah. So, if you plot here the true positive rate, right? And here you have the false positive rate. Let me make sure that I'm, because the notation changes. Yeah. So what we know is that this point is the one where you make the best solution for your classifier in terms of area under the ROC curve. So now what you know is that if you plot these curves, but independently for each of the groups, right? The point in which they cross, you know that the true positive rates and the false positive rates are equal for the two groups. And at the same time, they are going to be to the left as possible, which is what you want to achieve because you want to maximize your true positive rate. In the case of equal opportunity, it's a bit difficult from here, but in the case of equal opportunity, which is a bit of a less restrictive case, what you have is that if now we only care about the true positive rate. We don't care about the false positive rate because remember that everything that we wanted to achieve parity on was in true positive rate, right? So you can plot the true positive rate curve for each of the classes, for each of the groups, and then you can take this red one, which is the average between the ones for the females and the one for the males, right? Which is simply the average between the two of them, and try to find the one, again, the tangent, the one that is more to the left, and this is going to be the best solution or the most accurate solution that actually achieves equalized odds. Equal opportunity, sorry. Too many terms. Moving around. So basically, what happens is that this post-processing step can be applied in general to any classifier, any soft classifier, as long as it computes the probability of being in in the positive or in the negative class. And it's going to, in general, give a good relative performance between fairness and accuracy, because it's going to always find up to some error level because of your finite samples. It's going to always find the solution that maximizes accuracy condition on equalized odds or equal opportunity. So this is a good property, because then you don't need to worry about changing the classifier. You can simply keep your system as it was running, and in order to introduce fairness, simply change what threshold you are going to use to decide positive or negative. The problem is that it, of course, requires access to the sensitive attributes, because basically what we are going to do with this kind of post-processing is that we compute for every subject the probability of them reoffending, and based on whether they are a female or a male, for example, we are going to apply a different threshold. Because basically selecting a point in these ROC curves is no more than picking a threshold for the final decision in the soft classifier. And this is gonna be problematic mostly because under some laws and under some scenarios, we basically cannot use, due to disparate treatment, cannot use the sensitive features during the decision-making process. Also, it is a bit complicated because, as I said, this solution only allows you in general to find the optimal solution that fulfills the constraints, but not to navigate this trade-off between fairness and accuracy. So it's simply gonna solve the problem, the optimization problem here. Let me see if I can. This optimization problem with an equal to 0 here. So you cannot select a different alpha. It is equivalent to solve that problem. Also, something that some theoretical results from Woodworth in 2017 actually prove that under a finite sample of data, which is the general case, we never have infinite data when we train our classifiers, actually this approach is going to be suboptimal compared to the one that we are going to see next, which is directly training the classifier. It's a quite complicated proof, but they actually prove that this is going to work worse than actually changing the classifier. So in general, what changing the classifier means is exactly what I have been talking about before, and it's simply let's take our utility function, our performance objective function, let's say accuracy, and try to maximize it, find the parameters for the classifiers directly, while we fulfill some fairness constraints or unfairness constraints. I remark here again that if I make this alpha in this problem equals 0, basically I'm saying that you need to fulfill some sort of statistical parity, either in the errors or in the positive class. How does this translate? So if we would try to be achieving disparate impact, right, what I would like to do is to minimize the loss function of a classifier. Let's assume that I have a logistic regression, for example, with parameters theta, subject to the fact that once I make the decisions, the probability of making a positive decision for each of the groups is the same. This has a bit of a problem, and it is that, first of all, these probabilities can only be estimated empirically. So we might have not very good approximations for them, but also in some cases, for some classifiers, they can be very hard to compute beyond counting after making the decisions. For example, in an SVM, it might be something a bit complicated. Also, notice that, imagine that we have a linear classifier, right? Like the one I was plotting in the previous slide. So in order for these probabilities to change, I need to move some people from one side of the boundary to the other side of the boundary. But anything in between, if I shuffle these people around, as long as they remain in the same side of the boundary, nothing changes. That means that if I'm solving an optimization problem, for example, using gradient descent, quite popular nowadays, right? My gradient is going to be constant, actually, in general, 0, for any point that is in one side of the, it's going to be a constant for any point that is in one side of the boundary, and only going to be different than 0 exactly in the boundary, and then becomes constant again. That means, in terms of optimization, that basically everything is a saddle point until I cross the boundary. So, in general, there has been proposed in the literature are several relaxations for these fairness notions that were in terms of probabilities that actually leads to nicer or to less problematic constraints. Something that was proposed, actually we proposed in the literature, is that in many cases you have a classifier that is margin based, and everything that you have is that you imagine that there is a distance to the border of the classifier, and if it is positive, the distance, so if you are in one side of the margin, you have a positive distance that is proportional to how far you are from the margin, and then you classify as positive, and if you are in the other side of the classifier, you have a negative distance also proportional to how far you are from the margin, right? So you can exploit this property in order to relate these probabilities of being classifiers as positive or negative directly with the distance to the margin. And then compute some statistical dependence. In our case, is the covariance. It can be used also the correlation between the sensitive feature value and the distance to the margin. In the case of disparate impact, we only need to account for the distance to the margin for all the points, so that you would like to achieve that overall the distance to the margin in both the positive class and the negative class is similar for both sensitive groups, for the minority and the majority, whites, non-whites, females and males. In the case of other definitions that are based on errors, right, you don't want to account for them overall, but what you would like is that for the people that are in the wrong side of the margin, the distribution of the distance to the margin, like the expected value of the distance to the margin across groups, is the same. And this is something that you can achieve with this new function of covariance, which basically, instead of taking directly the distance to the margin, takes the minimum between 0 and the true label multiplied by the distance, right? That means if y and the distance agree in sign, right, this is a positive value. So we would be making the right classification. And if they disagree in sign, this would be smaller than 0. And then we would take the minimum, which would be negative. So this is in order to account for the errors, because we would only account for a value that is non-zero whenever we make an error. That is when the distance to the margin and the true label disagree. So the good news of this way of relaxing our fairness conditions is that actually these conditions, in the way we write them, are convex or concave convex with respect to the parameters of the classifier. So if originally we had, for example, a linear classifier, like a logistic regression, which can be, whose parameter we can learn solving a convex program, a convex optimization problem, right? By adding a convex constraint, our problem remains convex and we can still solve it in an efficient way. Similarly, while convex-concave solutions are not that nice, there is still a lot of work done there, and even Boyd, in his book and in all his implementations of the CVX, convex optimization, he has solutions that actually find the optimal solution with some provable warranties. In the case, of course, in which you have a nonlinear classifier, like a neural net, you might not be that interested in having convex constraints, but what you need is to have constraints that are differentiable and that triggers you to the optimal that you are trying to find. Otherwise, if your constraints are full of saddle points, there is not going to be a way of ensuring that. So basically, I'm not going to enter here, but of course, this covariance relaxation of our fairness constraints is just a proxy of these probabilities. There are many others, but in general, once we introduce a relaxation of these fairness constraints, we are also need to go and understand how of a relaxation this is and how much information we are losing by relaxing our constraints. In general, as long as you have a binary classification problem, in this particular case, the covariance is a good, or the correlation, it depends on how you compute it, is a good metric. But what we know is that if two variables are independent, the correlation is going to be 0. But the fact that the correlation is 0 doesn't need to ensure that they are completely independent. In the case of binary sensitive attributes, this is a very good proxy because both correspond to each other. So, again, I'm not going to spend too much time here, but of course, there is going to be a trade-off in this particular case, which is between the relative loss and empirical covariance, because the relative loss is what we were trying to minimize, and empirical covariance is what we will try to constrain on. And the more we reduce the empirical covariance, the more the loss we are going to have. This is, of course, going to translate into accuracy or discrepancies between our probabilities if we would try to achieve, for example, statistical demographic parity. Good. So, as I said, this has several good properties, which is, first of all, if you define properly your classifier, you are going to be able, and in some cases, like if everything is convex, you are going to be able to navigate this alpha parameter to control for fairness and move into the Pareto frontier between your loss and your relaxation of the fairness constraint. So this is going to be a very nice property because it gives us quite some control on which level of accuracy and fairness we can afford. Second, depending on the algorithm and how you have trained it, in general, all these kind of algorithms, they don't need access to the sensitive attribute during test. That means during decision making, and therefore you fulfill against this disparate treatment laws. The cons, which there are also, like everywhere else, there are also some cons, is that depending on the task that you try to solve, we have been seeing here only binary classification, and the algorithm that you train, how you need to solve this problem is going to change. Because if, of course, every classifier leads to a different learning problem, now if we have a to learn a classifier with some constraints, this is usually going to be an even harder problem than the original training one. The second one is that we are going to definitely need to change the classifier. So if you are a company and you have been working for years until you really manage to find the perfect classifier for yourself that was giving you the performance that you wanted, now you are going to need to retrain in order to account for these constraints. And the third one, which I hope it got clear, is that in general, these fairness notions that we studied yesterday, they cannot be directly incorporated in our learning as constraints because of several difficulties, but instead we need to rely on relaxations. We have seen here some one particular relaxation of these constraints. There are some others. You can have a look into the FAIR machine learning book. It's actually in a website that is fairmachinelearningbook.org. It's quite easy. And they are going to always have some problems because since it is being a relaxation and you are also working in finite sample sets, in general there might be a mismatch between what you would like to enforce and what you actually get later on in your data. So that said, during all this time, we have basically focused on fairness within a prediction framework. And not exactly a prediction framework, but a binary classification problem. Within this context, basically, all the criteria that we have seen is what people call observational. You have been talking about causality and causal reasoning last week. Also, Michelle was talking about this morning. And basically, what it means to be observational in this context is that basically all the definitions that we have seen have to do with the joint distribution between our set of features, sensitive and non-sensitive, our predictions, and our true labels, right? And there are many different configurations of dependencies between these features that can lead to the same joint distribution. Then there has been some limitations that have been pointed out in some examples, and this is why the community for the last couple of years, there has been more and more efforts at trying to connect causal reasoning and fairness in machine learning. This is due to, from my point of view, to two main reasons. First of all, because whether the information about the sensitive attribute or not is socially acceptable or legally acceptable to use is going to depend on actually how all these latent variables, all these variables or features that we have are related to each other. As an example, there was this example about the Berkeley College admission by Bickel, where basically initially what they thought is that they were having admissions for the bachelor program, if I don't remember wrong, and if they were only looking at the probability of women and male getting accepted, they noticed that women were getting less accepted than men. But then it turned out that women were in general applying to more challenging or more competitive departments, where actually the acceptance rate was much lower, right? So there was definitely a causal path between the sensitive feature, the department that they were applying to, and the decision, the admission decision that there was there. And then this was a starting point to start this debate about which causal graphs are allowed in each definition of fairness. So in this particular case, if we assume that Z is our sensitive feature, X is the department that they are applying to, and Y is the admission label for each of these applicants, maybe a path that goes from the sensitive feature to the department and then to the decision might be allowed, but not a path that goes directly from the gender to the decision that we make. The problem is that, in general, we use machine learning with a very high number of features, and knowing which ones or which are the causal paths between all these features and how they relate, how are the paths between our sensitive feature and our labels, is usually going to be challenging. Nevertheless, there are quite some work, and I think it's worth it to have a look to them. You have some information here. The other point, which I think is very remarkable, is that we have been talking about predictions all the time, predictions and predictions. But I always tend to say, okay, we make a prediction, but then we make a decision. And these decisions, in general, are some sort of an intervention. And we have seen, if you have been attended last week to the causal reasoning course, you know that interventions might shift distributions, might have an effect in what you observe. And this is exactly where I think it's important to remark that we do learning, we make predictions, but then we are going to make decisions. So, and these decisions, in general, and we were talking about that also yesterday when I said ground truth, non-ground truth, do not necessarily need to match the labels. So as an example, if we come back to our example where we have defendants in a pretrial bail scenario, then in general the decision is going to be whether we release or not the defendant from jail before the trial. But the label is going to be that given that we have released that defendant from jail, whether he reoffends. So, for example, in the Compass data, the label was whether the people reoffended after 2 years from release. Under this scenario, you can represent fairness as the difference between what we call benefits, which is some other way of writing these fairness notions that we had before in terms of expectations. But by making, and importantly, by making this distinction between predictions and decisions, what we need to know is that maybe prediction loss of accuracy is not what we need to look at, but instead we need to look at the utility or the reward of the decision that we make. So some quite used definitions of utility in this context is the one that we have here, where we take the expectation over our population of this expression, which has two terms. One that can be seen, the first one on the left, that can be seen as something proportional to the number of crime prevented, and the second one that is proportional to the cost of keeping people in jail. The thing is that it can be proved that if we solve without any constraint, we try to find the policy under which we make decisions, and there's this utility function. What we find is that the optimal decision rule is a deterministic policy in which we keep someone in jail if their probability of reoffending is greater than the cost of keeping them in jail. That can be easily seen because basically in this utility, I took the expectation already with respect to y, so that now instead of having y here, I have the probability of reoffending. And now you can see that this term becomes positive, so it increases our utility. If P of y given z is greater than c, otherwise it is negative. Okay? Similarly, if we extend this formulation to maximize our utility subject to some fairness constraints, which in this particular case I have written in terms of benefits, which is the expectation of some of the functions with respect between z, y, and y hat, we can again rewrite the optimal decision rule as a deterministic decision rule, where decision policy as a deterministic decision rule, where we are going to release someone from jail if the probability of reoffending is greater than a threshold that this time is going to depend on their sensitive attribute. Because basically, before we have the cost of keeping people in jail, but now we are going to need to correct for this threshold across groups so that we correct and make, for example, enforce statistical parity. We make these benefits to be the same across groups. And since these benefits are going to be an expectation, which is going to depend on Z, we might need to correct for one side or another. Of course, what this optimal decision rule assumes is that this probability is actually known beforehand, right? But as a machine learner, you have a probability, but you don't have access to, but you got data, so why not to estimate that from observations, right? And this is exactly what we are going to see, that some of the problems and some of the effects of interventions actually come in. So imagine we get data, we do the learning procedure, and then we get an estimate for this probability of reoffending, and based on that, we implement the policy that makes decisions not based on the true probability of reoffending, but on our estimation, right? We deploy this decision policy in order to collect more data. And of course, the more data we collect, the more we can refine our prediction, right? So we could close the circle. The main problem here is that the data that we are collecting actually don't come from the true population distribution, but they come from a distribution that is induced by the policy that we have implemented. That means our sample is might not be representative of the population. And all these statistical learning theory results that are very nice, that the more data that you collect, the lower the error becomes, don't hold here anymore. And this is exactly what we actually prove in some of our recent papers, where we actually show that under the lack of knowledge of these probabilities, or in general, by having only finite samples, data, you cannot implement during learning or during data collection deterministic policies, because they will never ensure that you will convert to the optimal policy or decision-making system, not in terms of accuracy, but also not in terms of fairness. Somehow these results are quite correlated with some of the results that are already well known in the literature, for example, on reinforcement learning, but somehow they were completely ignored in the fairness community. So, simply to show you some visual examples, basically what we do in these plots is to actually keep collecting data, navigating around this full closed loop that we got here, and implement either deterministic policies of the sort that I was showing before with your current estimation of the probabilities of reoffending, or apply some stochastic policies. And what we can see is that by having a deterministic policy, if this is our optimal utility, and this is our optimal level of demographic parity and our optimal level, optimal in the sense that it is the ground truth in the data set. We are not imposing any fairness constraints here. What it happens is that you can see that the orange line, which is the deterministic policies, they are far away from the optimal solution. So they are not only suboptimal in terms of accuracy, that means you get lower accuracy that you would get with the optimal policy, significantly lower, but they usually tend to amplify the unfairness, because the level of unfairness in the true data set or in the original optimal decision-making system is this black line, and we are way above it. So we need to be very careful about how we are doing the data collection and how we are training our systems, because these kind of effects where it is not that our system is unfair, it is our system is over time amplifying the level of unfairness and being also suboptimal in terms of utility, because simply we map a problem that was not a classification problem into a classification problem. Good? So just to finalize, basically, as a big summary, and if you only take a few take-home messages from our data, from our talk, in fairness, basically remember that observational criteria and approaches might be useful to point out unfairness, but might not be enough to completely avoid it. Causal reasoning may help in this framework, but somehow it's quite complicated, because having the causal graph and the causal dependencies in our high-dimensional set of features is usually not going to be very easy to obtain. And something that we never should forget is that features are no more than some measurements that we take from the world to represent it. But we need to account for how these features have been measured and what they represent, right? Because it might be that we saw that these features might be only representative for some group of the population, but not for others. And also, during the collection process of these features, we are performing some sort of intervention that is breaking down any of the theory that we knew. Okay, so with that, I basically conclude the fairness part. So it is a good time if you have questions. Otherwise, I will jump into interpretability. No questions? Is that the question? No? So, let's assume now that finally we have solved the whole scope from before, and maybe we have a system that works quite well. Right? So the next question would be, how does the system work, or why a decision was made? This is basically what the goal of interpretable machine learning is, and it can be divided into many different levels that more or less I'm going to try to give you a general overview. So before I go into details, I would like to point out that I got this slide with quite some help from one of my students, so I think I should give him some credit. And let's assume that we have an example which we have already been discussing, which is we apply for a loan. And then there is an algorithm that decides whether a loan is granted to me or not. So this is a decision made by an algorithm that may have significant consequences in my life. But this is not the only example. We can think of many others, like some of them we have discussed, like university admission, insurance policies, some pretrial bail, job hiring. So quite of them are significant and they have an impact not only on the individual but also in the society. So the goal of interpretability is to understand why these decisions are made by an algorithm. Of course, the first question would be, we have been talking about fairness, and the first thing that we did was to define fairness. And actually we define fairness as discrimination in general. So in general, interpret is usually referred as the ability to explain or to present in understandable terms. Together with that definition, in the machine learning literature in some of the recent years, some others are a bit older, they have tried to formulate this interpretability definition in a bit of a more concrete way. And within these definitions, what we are going to do is that we are going to take the definition by Isabel from Harvard and Bin Kim now in Google, which is the ability to explain or to present in understandable terms to a human. Because we are trying to explain an algorithm to a human, right? So, not such a surprise that the ability should be through a mechanism. So before, when we were talking about fairness, we had a whole section that was mechanisms. To explain, explanation is actually the definition, right? It's actually what we need. What is a good explanation is actually the measure, which is understandable terms, and the human is going to be the stakeholder to whom we are giving the human the explanation, who needs to understand that explanation. So basically, depending on the framework, all these mechanisms, definitions, and measurements, and the stakeholders involved are going to change quite a bit. So you can imagine that in general, it's going to be quite hard to have a general framework that accounts for all this all together. So, but let's start with the stakeholder to get a better understanding of who the human might be. So the first stakeholder might be to do with the system administrator. So let's imagine that we have a designer of the method and we have somehow the company that is deploying it. Then, of course, we might have the users that this system is applied to make decisions, the loan applicants, and of course, by the end of the day, if an applicant for a loan doesn't get the loan, he might go to court and say, I didn't get the loan, I think this is not okay, and he can contest, and there might be a justice system involved making the decision where this decision was properly made or not. So, as you can see, the type of definitions of the goal of definitions that these different stakeholders might require are completely different because, for example, the developer might be more interested in how the overall system works in order to do some debugging and improvement. In terms of the system administrator, he might be more interested in terms of the robustness, the privacy and accountability of the system to know, okay, I'm the last responsible for this system, so is it behaving as it should be, right? From the level of the applicants or from the level of the users that these systems make decisions on, it might be more interesting to know why a particular decision was made. Why didn't I get the loan? And from a justice system point of view, it might be interesting to know whether the system is aligned with our current laws. So you can think that we got 4 different groups, and you can think already of at least 4 different types of explanations, and all of them are different. So we can divide them a bit more into 2 groups, one that is more about verification during deployment, what you expect from the system, and the other one that has to do more with validation, which is, okay, is it aligned with society, with our ethics? And this is directly related to trust. So before we are able to completely deploy these systems and trust them, we need to make sure that they are aligned with our ethical requirements and laws. So coming back to definitions of fairness, there are like a few. They keep showing up here. So all these definitions and quite a few more has been discussed and defined in the literature. In general, I usually like to divide them into 2 groups, one that has to do with transparency and the other one that has to do with explainability. Basically, when we talk at the level of transparency, what we would like to know is the overall functionality of the system, right? That's why we call it a system to be transparent, because it's like you have a look to the system and you get a general idea of how the system works. While at the level of what it is called explainability, what we would like to understand is the individual decision, the overall decisions made by the system, not directly how internally it works, how many transformations the system has inside. If you have a neural net, not exactly which neurons activate at any time, right? But more why this overall network arrived to a conclusion, arrived to a prediction or to a decision. Of course, I think it's quite intuitive to understand that when we talk about transparency, we are talking about the level of the model, the whole algorithm, while when we talk about explainability, we usually talk more about the outcomes. In this particular case, I'm focusing mostly on decisions. So once we have 2 high-level definitions of interpretability, we stick ourselves to transparency, and to explainability, one would like to get, as we did with fairness, a quantifiable measure that we can quantify from observations. Unfortunately, that's not quite possible yet. So we don't have a single objective measure of interpretability in the literature that has been adopted. So we don't know how to compare different explanations. We don't know how to compare different interpretations of our model. What we do actually know from the social science literature is that these explanations need to fulfill 3 main properties. One of them is to be constructive, they need to be selective, and they need to be social. So constructive in general means that they need to explain why a decision was made instead of another one. This has been proved socially talking that it's how more or less we like to understand decisions. Selective, they mean that it should be specific for the problem that you are trying to solve, right? So that brings us to the stakeholder problem. So it should be useful for the goal that they have in mind. And social means that it needs to be understandable by a human. It needs to be something that you can communicate with. In terms of measures, we don't have a metric, but what we have is different levels of abstraction. So you can have explanation at the functionality level, which is, as I said, very related to transparency. At the human level, so we try to give an explanation that is understandable for a human, for example, for the doctor that we are presenting these results, or application grounded. We put the explanation into a context and we say this diagnosis is the one suggested by the algorithm, y is this diagnosis suggested by the algorithm. In the human one, we would be talking more about the patient. So, in terms of mechanisms is when we can have a bit of more discussion. What we can divide again is these mechanisms into different groups. One is towards transparency and the other one is towards explainability. So basically, what we have here is that if you go to the literature, there is not clearly an agreement on how these different mechanisms of fairness should be classified. So between Amir, my student, and I, we were reading forever many papers until we decided to structure these mechanisms into these groups. So in terms of transparency, we are going to divide them into simulability, decomposability, and algorithmic transparency. We are going to see examples later. And in terms of mechanisms of explainability, we are going to try to give explanations about the outcomes based on features, based on instances, and also based on what they call surrogate models. Everything is going to be more clear in the next few slides. So, of course, if we make a line connecting these explanations, what we have is that when we go more towards transparency, we have some solutions that are more model specific, so they depend a lot on the model that we are using, the algorithm. They are at the level, at the global level, so we try to understand the overall functionality, and usually they move towards transparency. The more transparent the system is, the more white box it is. I think it's not very necessary, but since it is quite clear that when we refer to neural nets, we often refer to them as black boxes. So somehow transparency and neural net seems to be against each other. When we go more towards explainability, what we are doing is to move towards model agnostic explanations. So it is not a matter of exactly how the functionality of the system is, but how a particular outcome, why a particular outcome is decided. Of course, this is a local explanation because we take one outcome, one prediction, and we try to explain it. And it can be applied more to black boxes. So in this graph, basically, I don't remember from, I think it's from the book of Interpretable ML, I forgot to add the reference. What they do is that they took, like in a graph, they plot on one hand the model accuracy and on the other one some sort of measure of explainability, and they plot the different very common predictive systems in machine learning into this plot. And as you can see here, we have as the most accurate systems, deep networks, which tends to be, according to this plot, the least explainable one. I'm not quite sure about this plot or this graph to be really the right one, because there is a whole debate. Because depending on how you measure explainability, whether you are more into transparency, definitely a neural net is not transparent, but maybe you can make it explainable. So there is a lot of discussion here. And also when you look at decision trees, people tend to think that decision trees are highly explainable. But if now I run a decision tree over 100 features with I don't know how many levels in the tree, is this still interpretable? Can we still parse a very huge tree? Well, I'm not that sure. So, coming back to our mechanisms, if we start with one particular type of transparency, which is simulability, it's called simulability, what we can think of is kind of rule-based algorithms. So basically, the goal of a rule set is basically explain or design systems that are already transparent and interpretable. And basically what they are going to do is to make decisions based on a set of rules. You can write, for example, a decision tree as a set of embedded rules. As here we have an example, you can come with any other example, but let's imagine that we are trying to classify people and we say, okay, if someone is a computer scientist and a man, he is into machine learning, right? If he is a computer scientist, but is a female, probably is into bioinformatics, and so on and so forth. The problem of that is that, of course, the more features that we collect, the more complex these rules become, and also you need to have quite complex rules in order to achieve very high accuracy. So this is the main limitation of this building directly these transparent systems, that you are enforcing yourself to remain very simple so that they are interpretable, but then you might not be able to achieve the same accuracy that you would achieve with a neural net classifier. So the second way of performing transparency that enforcing transparency that doesn't need to be enforced directly in the design of the system is to actually do feature visualization. I think by now probably several of you should have seen some articles on that line. Usually this type of transparency or explanations are mostly thought for neural nets. And when I talk about a unit, I can talk about many different things. I can talk about a particular activation. I can talk about a channel, a whole layer. Yeah, there are like an infinite number of approaches. And in general, what you would like to know is that what is this particular unit paying attention to in order to make the prediction, right? The problem of that is that, in general, these kind of solutions are only suitable for images, right? Because otherwise, basically what they are doing is visualizing units in a neural net. So as long as we cannot visualize them, that's not very useful. Something that they lack, of course, is from semantical concepts for humans, right? So this is why it works with images, because when we see an image, we can maybe understand, but if we do that with text and we simply plot the activation of a unit, of a neuron with respect to text, we don't manage to do this mapping between text and the activation of the unit. Also, as I was pointing out before, you have plenty of units, or you can represent this, you can visualize these networks in many different ways. Usually this has been mostly used for CNNs, so it seems to work quite well in images with CNNs, but that's it. And basically the problem also is that they ignore correlations or dependencies between the different units. So once you make a decision about which level of visualization you are going to use, you are ignoring any dependence with the rest. So if we now move from transparency to explainability, there is a similar, there is a feature-based explanation, which I think probably is familiar to several of you, which is which part of the inputs are more important in order to make the decision. As an example of that, basically what we usually have are saliency maps and all the variations around them. And basically what they do is that you take, for example, an image, and in order to decide whether there is a dog in the image, they point out which is the part of the image that had more weight into this decision. There are many different ways of doing that by simply building up some linear approximation to the model, tailored expansion around the particular image, and propagate the function so that you get the importance of the input space. The problem is that, first of all, if it is only suitable for images, that doesn't need to be that problematic because we are using these methods a lot for images. But most importantly, what there is quite several works that actually challenge the reliability of the explanations provided by these systems. So, in particular, oh, I don't know what I did, I'm sorry. Yeah, in particular, I pointed out here 2 papers where basically, depending on the reference point that they were using in the image, they were getting completely different results with the same method based on, in terms of which parts of the input space were more important for the decision. So they have a lot of studies, but so far it doesn't seem to be very robust in the explanations that they gave. Also for me, from a point of view, I have been exposed to several explanations where they have different types of buildings and they say this is a dome, this is a church. I didn't see any difference. It's something I cannot parse, but maybe I would need to be an expert in architecture. And the last type of explanations that we are going to talk about is actually very related to something that Michelle was talking this morning, and they are counterfactual explanations. So here, in terms of instance-based, when I mean instance-based, basically you can give an explanation based on the input space and at the level of the observations that you have. So there has been proposed initially, for example, by Bin Kim, some approaches in which you could get prototypes. So you make a decision in a classifier and you, as an explanation, you say to someone, you got classified as dog because the closest image to your image is this one and it also has a dog. Then they thought that maybe this kind of explanations, prototyping was not enough, and then they also, the same Bin Kim from Google decided to incorporate some criticism. That means they provided some, what we call before constructive, not constructive. Let me see. Suddenly I got the word wrong. Okay, so basically they said you got a dog because you are similar to this dog, and also because this other image is very far from you and has a cat, right? So you get this kind of counterfactual explanation. So I think these counterfactual explanations can be seen a step forward where actually what you would get, and it doesn't need to be within the image, is that you were denied the loan because your annual income was whatever, and you would have gotten the loan if your annual income would have been increased by some amount, right? Constructive. So in this setting, what a couple of years ago, the collaboration with some machine learners with some researchers from the law from Oxford proposed is to use something that has been highly studied in philosophy, which is actually counterfactual explanations. And actually, what they focus is on the nearest counterfactual. And this is no more than what would you need to change in your input space in order to get the desired outcome. But as the nearest, you want to make, of course, the minimal changes in your input space, because maybe changing from 30K of salary to 45K, it's hard, but maybe doable. But if I say that you would need 100K, maybe things become a bit trickier. So what they usually do is that they can write this counterfactual explanation as an optimization problem, where basically what you get is that you need to find, this is the factual, so the original data point, and you just need to find the counterfactual explanation by minimizing the distance between from your input space to the general input space, such that the outcome is different between the factual and the counterfactual. So for example, in our binary case, I didn't get the loan. What is the minimum change I need to do in my set of features in order to get the loan? That is exactly what this optimization problem means here. Of course, it may happen that this counterfactual explanation, let's imagine that we come back to the COMPAS data and you say you were not released from jail, right? because you are Afro-American. If you were white, you would have been released, right? Maybe this kind of explanation might be useful for the justice system, but if you give this explanation to the defender, might be quite problematic because it's not plausible. We cannot ask people to change their race, their gender. Also, they cannot get younger, or I cannot get 2 meters tall, right? So this is something that, in general, we need to incorporate in what we call plausibility constraints. For those that are familiar with adversarial examples, for example, in images, in general, what you want when you find an adversarial example is to find the minimum modification in the image, right? That gives to an error into the outcome, but it is still plausible, right? And in general, plausible in this meaning, in this sense, just means that actually I still see a cat. Our visual perception doesn't change. So these kind of counterfactual explanations or adversarial examples are actually quite related, and there is not much, but some literature that actually relates the two of them. So, in terms of generating counterfactual explanations, there are quite a few in the literature. Many of them, they are only restricted to linear classifiers and linear similarity metrics. Something that I haven't pointed out, but I think it's important, is that when we are trying to give explanations in terms of counterfactuals and solve these previous optimization problem, we are assuming that we have a similarity metric in our input space. But as we were discussing yesterday when we were talking about individual fairness, that might be challenging in some applications. So let's assume that I have a distance metric and I have a classifier. Most of the approaches out there, they only assume linear classifiers or differentiable classifiers and distances that are linear. Also, many of them, they don't have, at the moment the classifier is not linear, they might have not guarantees on whether the counterfactual that they found is actually the nearest one. It's the one that solves the optimization problem, because if your optimization problem before is non-convex, then finding the global optima might become quite difficult. They also assume very homogeneous features spaces. That's also a bit challenging because in most of the applications that we have been talking about, people, for example, applicants 2 alone, they are defined with a set of features. We have very different statistical properties. So definitely my age, my gender, and my income, they are different type of variables. They take different domains, they have different distributions, and therefore they should also have different similarity metrics. But the thing is that how do I mix them, all of them together, is also a big deal. Also, when we talk about plausibility, which is when we generate a counterfactual, how plausible this counterfactual, how useful this counterfactual explanation is for the subject to take an action is something that we need to account for. But for example, maybe I'm not able to ask someone to change their income without changing their education, because the more, depending on your education, on your expertise, you are going to have different income if you are lucky, right? So something that hasn't been yet included there is actually any type of statistical dependence between the input space, how they are related. Maybe I'm not able to change my body mass index without changing my weight. Definitely my height, I cannot change it. But also, for example, the causal graphs in your input space, right? You might not be able to change one feature without changing the rest of them if there is a hierarchy in your graph. So basically, while there are some definitions of interpretability, something that I haven't managed to show you is any measure. That means that in general, whenever we have one of these mechanisms, how do we compare the explanation that they give us? In general, that's like, yeah, it seems to be a good explanation. But we don't have a quantifiable measure that says this explanation is better than the other. We haven't managed to find that solution. Second, in general, we have seen that many of these approaches are restrictive to a particular task and a particular type of data. We have seen that many of them, they are only for classification and for images. And the ones that are useful for classification and images are not useful for other type of data, and in the other way around. So, knowing which type of mechanism and explanation is useful and when, it's still an open challenge. The other problem that we have discussed is that the dependencies in the feature space, they are also not taken into account in most of these explanations, but they simply assume that you can change the feature space in completely independent ways in order to get an explanation, and that's it. It's like finding the most important pixel in an image without looking at the neighborhood. That wouldn't make any sense. And only very recently, some works have tried to include some semantical concepts into these explanations. Again, only applicable in the context of images, but in general, we don't know how to incorporate this information so that when we have a mechanism to provide an explanation, this explanation has some semantical meaning. Also, one may wonder why do we need explanations. First of all, it might be important for us, but also there has been quite some discussion about interpretability as a proxy for robustness, fairness, and other ethical concerns that may arise from systems, because it's a way of trying to understand how a system will behave when we deploy it. So, basically, if there is something that I believe we should take home, and I started my presentation yesterday like that, is that when, oops, that's not what I wanted. When we are actually going to design and deploy methods in the real world, and especially when we are going to use them to make decisions about people, it is not enough to assume that I was given the data, I train a classifier with, and if I have 99% accuracy, I'm done. But there are many other factors that you need to consider. We have seen some of them. We have seen fairness and how many things can be wrong, how challenging it is actually to incorporate. I don't know why you are seeing this. You should have told me. Okay, let me see. Yeah. So there has been a lot of things that can go wrong, and even starting for how. No? No. Okay, on how these features, how representative these features are, how for different groups of the population, how they relate between each other, whether there are some causal graph between them, whether there are some statistical correlations, how this data has been collected, whether they are representative or not, whether we are making some interventions that might have been shifting the distribution that we got. All this is going to have an impact in the results that we get, and it's going to imply a strong mismatch between what we expected while development and what we get under deployment. So it is really important that we stop thinking about all these methods as simply as classifier, and we only focus on, I got 99% accuracy, I'm done. But we need to try to understand whether these methods to make decisions, mostly in the context that we have been discussing, are actually aligned with our laws and our ethical rules. And with that, I would like to conclude, and I'm happy to take any questions for the next 4 minutes. Thank you.